que eres el artífice de la idea. Vale, creo que ya debemos estar.
¿Sí?
Sí, no, que ya debemos estar en directo, así que cuando quieras.
Adelante. So, good morning, everyone. Thank you for joining this special or this invited talk that we have today. We are very happy to host Guillem Anglada with his talk about Mars, past life and future life. I hear some, yeah, well, it's okay. So just a brief introduction about Guillem. He's working in one of our neighboring institutes here in the campus. So the Institute of Science, Ciències de l'Espai from the CSIC. And actually, since 2019 as a Ramon y Cajal scientist. Before that, he studied physics and got his PhD in the Universitat de Barcelona. And then he did some postdoctoral stays in USA in the Carnegie Institution, and then in Germany in the University of Göttingen, before getting a reader position in astronomy in the Queen Mary University of London. So his PhD work was related to ISA's Gaia mission. And then he started working as a postdoctoral researcher more on the precision techniques on exoplanet detection. So you may know his work or heard about his work for a great achievement in 2016, which was the discovery of Proxima b. So probably he will also talk a little bit about that. And then he has been, let's say, continued working with instrument development on high resolution spectrometers. He's also very committed with science communication and has promoted a number of initiatives, as you will see, and also he's recently, or since 2018, one of the main persons in charge of a project called Newell, which I think we will see some of the things today on Mars colonization. So yeah, without further ado, I leave the stage to Guillem, and I hope you all will enjoy his presentation.
Okay, thank you. I don't see myself or you, so I hope I'm on the screen. Okay.
Yeah.
Hi, thanks, Gemma, for the invitation and the Institute for this initiative. We hope to see one of your talks in our institute, I think, right? In a few.
Yeah, I think in the fall season, we will do this kind of exchange.
Yes. So yeah, also, I have to say that our institute, not a lot of people is working on what I'm going to show you today, but anyway, it's something that we are involved, and there are a number of collaborations going on around this. It's also a nice, or let's say a light topic to stimulate discussion, and especially to start conversations with people from different disciplines about space exploration. But also, this is very important because sometimes we see this kind of talks or this kind of talk about going to Mars, colonization, or using or going, I don't like the word colonization, but let's say create permanent settlements, long-term sustainable settlements on space. That's very important keyword because as Gemma was saying, I've been working a bit on this idea of eventually, if we want to make a qualitative, a quantitative jump in capabilities, we should start operating in space, let's say, being able to manufacture, being able to do more complex operations such as sending satellites and doing things, but actually having permanent human presence. It can be in the form of an observatory on the moon. It can be a large space station where manufacture and assembly of instruments can happen, and where we can do more advanced experiments, and also things related to industry that can have direct returns to Earth economy. So this is a bit of the goal of a network that we created. It's called SONET. It's called Sustainable World Network, and it's a collaboration between academics and people from the private sector as well. We are about 40 people, and we are growing. I would love to invite anyone who wants to join, which I will do at the end, but we are in the process of scaling up, and we are not very good at this. We need a bit of more administration, organization, and support. So we can discuss a bit later and can tell you more. But within this collaboration last year, there was a call for the Mars Society to try to think about a possible city, how a possible city would develop on Mars. And it's not about only going there and deploying a city and listing all the technologies, but trying to figure out, or at least this is what we tried to do, try to figure out if it makes sense at all, at least from a technological sustainability point of view, but even from a social point of view, because it's not a matter of putting a station in Antarctica or somewhere else where you maintain it and you just use it for operations. But here we are talking about a bit more long-term settlement and something that can be sustain itself. It doesn't need to depend on resources continuously being fed from Earth, because that's not a very long-term sustainable thing to do anyway. Okay, so this is what I'm going to talk at the end. This would be the future life, but let's put a bit why Mars is this very special planet that it's very much in the news, and it has to do with Mars as a potential site for past life. I'm going to introduce a bit the planet Mars. Here you see the three states of Mars. In the past, Mars apparently, and as you will see, was a very wet world, much similar to Earth. And currently, this is what we see now in the center. Mars is a red planet because it's covered in mostly iron oxide. It's a very thin layer, maybe, but it makes the planet look red. And maybe we'll see what happens in the future if it becomes a populated planet again. So very general, very quick also. The solar system, for those that you are not familiar with, has the 8 planets. In the outer solar system, we have 4 gas giants because they form that way in there. It's a matter of that volatiles, essentially gases, need to be available when the planet is forming. And in the inner parts of the solar system, these gases are wiped out early. So in principle, this is why only the rocks, let's say asteroids and small bodies are left when the star starts to shine and starts to remove the gas out around it. And this is why we have these 4 small planets in the inner parts of the solar system, and outside there are the gas giants, but very much outside. So let's say Earth, it's at the distance of the sun called 1 astronomical unit. To give you a sense of a scale, is 1. If Earth is the scale, Earth's sun distance, the gas giant Jupiter is at 5 astronomical units, Saturn is at 12. So the scale is very different. It's really the inner solar system is a compact part, and the solar system at large is a much extended thing. So we are going to focus on the 4 inner planets, which are relatively similar to each other, especially the 3 outer ones. The inner one, it's Mercury. It's a bit different because, again, it's so close to the sun that things that evaporate are much more than in the other situations. But then Venus, Earth, and Mars form more or less of the same materials, and therefore, at the beginning, they may have had very similar conditions. Even Venus today is a very hostile place for life, but now there is the talk, and NASA actually is planning to launch a couple of missions. It's been said that maybe Venus was still habitable a few 100 million years ago, until very recently. So, and the issue is why, even though these planets are similar, why, for example, they are in very different states. So Venus is a different story for another day. It went through something called runaway greenhouse effect. The Earth is what we have now, is what you know. You also know that we are going into a greenhouse effect. If it's runaway or not, we will see. And then we have Mars, which looks different from the other 2, in the sense that its atmosphere, for example, it's much less dense. And the reason for this is Mars started more or less like the other 2 planets. One thing I would like to say, that there is a misconception. Both Earth, Venus, initial Venus, and Mars, they are very dry worlds. So Earth has very little water in composition, in mass. It's less than 1 part in 1,000. The thing is that water, because it's lighter, it accumulates on the surface, or it integrates in the minerals, but doesn't matter. So, but the mass in water on Earth is already very small, and for Mars is a bit more or less the same. Water is on the surface of these planets. It started there probably by delivery of comets and asteroids, not from the initial water composition, because that water probably was lost. But anyway, so this planet started with some water. Mars was a bit more outside the solar system, therefore it was cooler, so it probably started as an ice ball planet. Imagine a planet that it's completely covered by probably frozen water, probably a couple meters of frozen water at least. And at some point, Mars started, similar to Earth, had a lot of volcanism, which released a lot of greenhouse gases. So for the, let's say, for the first 500, 600 million years, Mars had oceans on its surface. And it's not, we know that now for sure, that we saw that there were rivers and there were kind of canals, and there's also an hemisphere of Mars that has no craters, which means that the surface is much more new than the rest of the planet. And this has to do with the fact that water, of course, if you have an ocean, it would erase craters. It's like why we don't have craters on Earth. It's because the atmosphere and the climate are continuously operating on it, and also the plate tectonics. So Mars had an ocean covering probably one hemisphere and several other places. It was all going well, but at some point, because it's smaller, it cooled down and the interior becomes solid, and it lost its magnetic field due to this. And also the volcanism stopped, so no more greenhouse gases were released or cycled. And what that made is that the planet went into a runaway cold trap thing, because the water freezes, the CO2 also freezes, and then it reflects more light. And at some point, the temperature starts to go down, and you end up with a frozen wall. Some of the water probably was lost in the process as well. And this has been the mainstream theory for a long time, but now it's changing a bit, because water is lost when you lose the magnetic field. UV light destroys the water molecule, and the solar wind removes the hydrogen because it's very light. And what is left is a wall that it's more rich in oxygen, because you have the leftover of the water molecule. And you lost some water, but also the temperature drops, because water is a very powerful greenhouse gas also. The Earth, the more powerful greenhouse gas is not carbon dioxide, it's actually water. But the water you cannot get rid of, and then the CO2 is kind of added to the greenhouse. This is what's the problem on Earth. So on Mars, this combination of factors made that the planet froze about 3.8 billion years ago, and it remained like this since then. Essentially hasn't changed much, which is also interesting from the point of view that it provides like a frozen record or fossil record of a planet that started very much like Earth, and maybe life started there, because this 3.8 billion years, when the planet was still humid and had a lot of water, this is when life also started on Earth. So in principle, the same conditions, even the volcanism that gave birth to life, they were also present on Mars, especially CO2. If Earth had no life, the atmosphere would be mostly composed by CO2. It's a very stable molecule, and it's a gas. At the distance of the sun, it remains as gas. And Mars, for example, Mars' atmosphere is CO2, and Venus' atmosphere is also almost pure CO2 plus other things. So, and then if you have CO2, you have water, you have the three elements that you really need for life as we understand it. You need carbon, you need oxygen, and you need hydrogen. These three are the components. You have the energy, you have conditions where the water can be liquid, therefore life could have emerged. Now, if there is life today on Mars or not, it's a big question. We think, let's say it's a probabilistic argument, we don't know really, but I would say that chances are very low. Even though, and if there is life, it's not certainly an Earth-like life that has the ability of occupying all the niches available in the planet. We don't see on the surface activity. But we know that there are actually bodies of liquid water on Mars today, not on the surface, but underground. There have been detection of water in underground lakes. Don't imagine like a cave with a lake, but imagine like rock soaked with very salty water, which gives a very powerful radar return, which is how this was detected close to the Mars solar pole. And also in some regions, there have been seen these flows of seasonal flows of something flowing out of the outcrops, rock outcrops, that is changing over time. So a few months later, you can see that some canals were created, and then looks like salts remain there, kind of, all the water has evaporated and only the salts that were dissolved in the water remain. So this has been observed from the orbit by the several probes that are there. So we still have water today, which may indicate that still there are some conditions, at least underground, where life could be there. And another hint that maybe there is some biological activity is that Mars, from time to time, also seasonally shows outbursts, let's say, of methane. Not a lot, but methane is a molecule that if you leave it on the surface of Mars in the atmosphere, it's destroyed by the ultraviolet radiation, and it should not survive for very long. And we see actually that every season, every time Mars is a bit closer to the sun, there is a release of this methane, which this methane is geologically can be generated, but it's not easy. And then there's a hint with this underground water that maybe there is some organism in the underground making this methane up there. But it's again, it's tentative. It doesn't show that there is life, but there is some hints of life. In any case, it's this very residual life, not Earth-like life. So to figure out the origin of life or what happened with life on Mars, if it ever started, several missions are now ongoing. And one of them that you may have seen in the news is the Perseverance mission from NASA. And just to put you in context of things that are happening and you probably have seen, the good thing about Perseverance is that it's going into a crater that used to be a lake very long time ago. And we know that because we see a fossil delta where there are a lot of dejections from all the river that comes before that. And this is a good place because if it's like collecting a lot of geological samples from a very large area, these places are very good for geology studies and look for fossils. And this is a bit what we are there. Why we are there. NASA Perseverance is not going to try to find current life, it's going to look for fossils. And essentially, at least initially, is designed to try to look for microscopic evidence, to try to find patterns in pictures, essentially, and also do some chemical probing to see if there was evidence of organic chemistry. So yeah, that was a picture from the orbit, but we are now on the surface of Mars. This is from this Jezero crater, and you can see here these mountains on the back, and here close is this delta river, and all these rocks here are here for observation. Eventually, Perseverance should go on top of these places and try to find fossils. Again, it's looking for microscopic things, but maybe finds macroscopic objects like a leaf or something that looks like a leaf or reminds of an algae or something like this. That would be groundbreaking for sure. It can happen. So that's the thing. Maybe it doesn't find anything, but it could happen, which is exciting by itself, I think. So good. So we know where we are now. We know that Mars is exciting because of the origin of life. A second origin of life would show that if the conditions are correct or right, life can start in any place in the universe. And there are a lot of planets like Mars and Earth around other stars. This is my other research topic. We basically know that 50% of the stars typically have Earth-like planets. Therefore, if these conditions are right, and every time the conditions are right, life emerges, this would mean that the universe is a very crowded place. And we would probably not be alone. What kind of alone or what kind of life, that's another story. But anyway, so also just focusing on Mars, the question then is, okay, Mars probably was habitable, maybe life could have emerged. And the question is now, could we also eventually move? No, not move in the sense of going and saving humanity and moving it to Mars, but could we also start civilization, let's say on Mars? Could we start something that is sustainable and independent from Earth? It's not, I'm not thinking out the super mega scale thing, but for example, a small city, a small settlement, something that can develop by itself independently of the home world, and therefore create again life on Mars that is able to be independent from Earth. Is it possible? That's a bit the question we wanted to answer. And this is the thing that we worked in Sonnet. We know, again, because it's very similar to Earth, we know all the minerals and the materials also. Raw materials are very similar. The only difference is that the climate is kind of frozen, in a frozen state. And then the question is, again, it's not a matter of going there and planting a flag with a rocket and then going back, which would be a very expensive mission. We assume that this can happen. Actually, if it doesn't happen, it's just an economic matter. It's not a technological impossibility at this point. But the issue is, okay, assume that this is possible. It might be demonstrated within the next decade, sending humans to Mars. But once we have done this, given our current technology, and I'm not thinking in an abstract way, I'm thinking about processes, things that we use to extract metals, for example, from the rock, to extract, process water to be consumed or produce and to be recycled. If we can use all this to think if we could, what it would take to put a settlement that is able to self-sustain its own growth with local resources only, that it's resilient in the sense that it's not super sensible to something happens, there's a sandstorm and the whole thing collapses or who knows what. And also it's a place where people would like to go, because that's another element of a settlement, let's say, or city. It's not that this is not a research outpost where people go there, make an experiment, come back, or an oil rig platform where people go to work. This is a place where people should go there and try to start a life, and it must have some incentives. It must have some life quality. They will not want to go there and start miserable lives. At least there is some promise. So it has to have this combination of factors. And if with current technology, we could imagine that this system is viable. And viable means that when you make the accountancy of all the resources, all the power, all the materials that are needed, all the social structure, if that budget, when you make it in detail, it converges to something that it's reasonable, let's say. It's not 10 or 5 orders of magnitude larger than what we can achieve on Earth. That was the exercise we wanted to do. And this is when Sonnet, this collaboration, we participate in the Mars Society trying to formulate a bit in a quantitative way how to solve this. And to do this, we proceeded in very engineering ways, if you want. There were people, urbanists, that work on developing cities on Earth, because the exercise is very similar. The only thing is that the conditions are different. But basically, it's like when you do an engineering project, you list all the functions that need to be satisfied: food, air production, air recycling, water recycling, manufacture, smelting of metals, everything, services, schools, hospitals, supplies. You put a list, and then you create a number of solutions that should try to overlap and satisfy all the functions. And if you succeed, you make a matrix. It has a name, I don't remember the name. But in principle, then you have a solution that is viable, and then you can assess how much it would cost. So that's a bit this kind of exercise using these design principles that I put here, these constraints. So the first thing that one needs to do, at least from my physicist point of view, I like to have equations also to be able to put numbers to things. This was important aspect. We not only want to look at the technologies, but actually quantify things. And this is basically a very simple model of growth, and you have seen it hundreds of times. It's an exponential growth where the growth, n, is the number of citizens, as a function of time, is basically proportional to n divided by a time scale. And this is not only the number of citizens, but it's also everything that you need to incorporate to the city to be able to add one citizen, plus some imports. Maybe you need some imports from Earth, some materials, some semiconductors, you have to try to minimize that, but anyway, they have to be there at least at the beginning. So you solve this differential equation, very simple, gives you an exponential. And if you plot this exponential, you can see, for example, if you have a development time of 50 years, we needed this plot to be able to actually compute the growth rate that you need to maintain in 50 years. And you want to go, for example, from 1,000 people to 1 million, you need to be able that each citizen every year is able to contribute to the construction of 0.12 city units. And I'm going to show you what a city unit is. A city unit basically is one person, and then all the resources that are required to be gathered from the environment. That would be atmosphere that needs to be processed, and also water that needs to be collected or obtained somehow, and minerals, but also the machines that you need to process all these water, minerals, etc. All the industry that you need to transform this into materials and products, and then all the services are associated to it, and these including agriculture, food distribution, hospitals, even schools, etc. So the key question then, trying to formulate the problem in a very quantitative way, is essentially trying to assess how much it costs to build one city unit and how much it costs to maintain one city unit, not in money, because at the end, the real universal current in these situations is energy, as you will see. You need energy to run all the processes, and at some point, energy, if you need too much, then you need too much infrastructure of energy, which also requires energy to be maintained, and the thing doesn't converge. So energy, at the end of the day, becomes the key element. Energy and materials, some of them. Okay, so the idea now is try to specify all the parts of the city, what each citizen would need to live, to get services and enjoy life, and then try to make a budget out of it. So the thing, this is a picture that of the city that we finally produced, and now it looks nice, but you don't know why it looks like this. So it's like a mesa with a lot of things on top of it, and then you can see like small dots on the face of a cliff, and you will see in a moment why this is the solution that we found. This is a solution. There are others, but again, it's an engineering process. It's not about finding absolute truth. It's just trying to find the solution and then evaluating if it's feasible or not. So why we had this architecture, and the idea is that Mars, different from Earth, has very different surface conditions, and you have to incorporate that. And the main issues, environmental factors, are that the pressure, you have to maintain always pressure, and it's very high. It's 1 atmosphere, 1 bar, and you need to prevent things to explode outside, otherwise people could not operate inside. So that actually it's the stronger physical constraint that you have. Then you also need to worry about the materials and the insulation, because the day to night temperature contrast can be very high. It can change up to 100 Celsius, and that not all the materials are very good at supporting this kind of pressure. Environmental pressure. Also, you need to protect the population from radiation, especially from the sun, but mostly from all over the sky, actually. From the galaxy, you have a lot of X-rays and gamma rays and particles. And for this, you need to accumulate material on top of the people, at least where they spend most of the time. And also protect against meteorite impacts. The good thing is that the gravity is 30% of the Earth. So actually your structures are not a lot of requirements. They can be much lighter once you build the domes or anything that can contain this pressure. The weight is not really important. But then also, for example, the solution that we thought that covers most of these things is actually built underground. And actually this is what we propose. But then you can have issues to access light, for example. So how we solve this is basically building the city on the wall of a cliff that it's rock, and it's facing south if you are in the northern hemisphere. So then you get sunlight going into apertures on the wall, and then inside the wall you can have these cylinders, these tunnels that the rock also helps you to maintain pressure, but also gives you thermal stability over the day-night cycle and also over the year. So this is the solution. This is just a schematic. I'm not going to a lot of detail because it has to be a bit short talk. So here, our city has 3 parts. There's a mesa, there's a wall where most of the city is, and there's a valley. And very quickly, in the wall, we will have these apertures, these cylinders that then gives you access to direct light. And then you can have gardens. Basically, people work and live in these cylinders. They are 10 meters long, wide to 100 or 200 meters deep into the rock. And then you can see that there is room for actually enjoying life and not just being in a tunnel all the time. Very quickly, pretty pictures. Also, this cylinder is not just, oh, let's put a lot of cylinders and then figure it out what to do. We had urbanists in our team, and they really wanted to make the city livable, which means that you must have your working spaces close to your living spaces and have gardens at walking distance and facilities, and etc. So it's like the Eixample or the Plaça Cerdà, but on Mars. In here, instead of making manzanas or apples, building blocks, we have these macro buildings which have all these cylinders interlocked with each other, where you have access to all the facilities, and then you have transportation horizontally via electric buses, let's say, and then vertically via elevators, because this cliff is about a kilometer. The good thing about this design is that you can have high density. The people don't need to move a lot to go to different parts of the city, but not occupy too much of the surface, for example. Okay, this is just, again, it's a modular solution that allows you to replicate and then move and copy the design, but also make it different and different parts. So not all the cities just copies of each other, like in an old communist city from the 60s, 70s. Okay, this is just, for example, from an office. You can see that you have access to the exterior, which is important for the psychology of the people living there, living quarters. So you have these tunnels, and then inside the tunnels, you have additional constructions where people live. And then in the valley, you would have, for example, larger spaces like communal spaces, like large parks, universities, hospitals, and so on. And this is just an example, for example, a tram station. And then on the mesa is where we would have the manufacture and the industry and food production. For example, these are just numbers. Very quickly, you need about 100 square meters to sustain a person. Let's say square meters means of garden or hydroponic, actually hydroponic agriculture. But most importantly, the most critical number here is that you need about 40 kilowatts. This is instantaneous power to keep people alive. And that's an important requirement that starts to become like a red flag to the whole design. This is a lot on Earth. This number is about 10 kilowatts. So at your home, maybe you consume about 2 kilowatts per person or 1 kilowatt per person. But on Mars, you need to actually collect a lot of energy from the sun and process it artificially to be able to feed the plants, which then fuel you, right? So all this overhead comes from this. Most of it comes from the life support system from feeding the plants to make food, actually. The diet of Mars, just for your curiosity, would be very vegetable, some insects as well in the menu, and a few animals also to act as buffers, because if there is excess of food, for example, you want to put it somewhere, it's the most efficient way to have animals, and for psychological reasons, it's good. And then everything has to be recycled, all the water recirculates, all the materials stay in the system. Nothing is thrown out once it's ingested in the city. This is just an example of a module with lights that are optimized to promote photosynthesis and therefore more efficient. And this is just a scheme of this thing that you saw. Now you know what it is. There are a lot of solar panels. They are needed because we need all this power, these 40 kilowatts to keep people alive, but also to keep the development rate that we wanted to grow in 50 years. You actually need almost 3 times that power. And you will see that in a second. Why is this? And then, of course, the city is not just the buildings, it's the people, but also a lot of services that need to be also thought and, let's say, put in the inventory and then work out how much they cost. Of course, taking people to Mars needs to be done as well. Don't have much time to do it, but this can be done also on Mars. The idea is that it doesn't consume Earth anymore because the same infrastructure in the city can be done for transportation can be done on Mars. And then you need a system for people to go there. Basically, they give all their possessions on Earth. That would be an ideal situation, but can be done differently. Someone pays for it. People go there. They got all the services. They got also what's called a Mars City share, which is like a share of the city. So every time there is a surplus, money is generated and is distributed with people that have shares. And that starts an intrinsic Martian economy, which allows people then to start their own businesses and build economy and Martian culture by itself. Very simple model, just to outline a bit how it's done. Also, this needs to be a very communal community because the environment is much more hostile. So you really need to be able to rely on your neighbors, let's say. And for this reason, cannot be the same individualistic Western culture that we have on Earth for other things. When you have all this, basically you can put everything in a pretty list like here or in a much boring spreadsheet, and then count how much materials you need per person for maintaining all this infrastructure. This is just a summary, visual summary of it. Don't need to look into details, just to show you that there's a lot of things. And then the idea, the exercise, final exercise with it is take the materials. We know how much they cost on Earth in terms of materials. We find the analogs on Mars, for example. Oxygen is not there, but we take it from the atmosphere, CO2, the water, for example, concrete. There are alternatives that can be done using the regolith in the surface. The metals, try to always use one metal. That's useful also for recyclability and reusability of everything. And so there are solutions essentially to everything. The only thing is that there are overheads on energy that it costs. So basically you put then all the overheads for collection, transformation, manufacture, and produce what you need. And this is kind of the summary of the feasibility summary, let's say. You conclude that to include one person on Mars, you need to locally extract about 1,300 tons of material. That seems a lot, but actually when you look at the numbers of Earth, it's mostly the same. Every one of you costs to society or to the planet about processing about 700 tons at least of materials into, most of the materials is actually rock to make streets and to make pavement, it's concrete and things like this. On Mars also you need about 80 tons of water and 100 tons of CO2 to be processed. The water actually is to extract the hydrogen, which allows you to do organic materials, plastics that are needed for domes, and also for a lot of daily products. And the big red flag of all this, actually these things are not that serious. The worst one is the power. Again, it's 120 kilowatts if you want to sustain this war, this development. And that's about 10 times more than what you need on Earth. Therefore, also means that people should have to work at least 10 times more, and the week has a number of days that you cannot work more than that. Therefore, to really enable this settlement on Mars, the one thing that we need for sure is a lot of support from, let's say, standardization of industry, standardization of processes, and a lot of AI support and design things to be operated robotically. Don't create a farm and then put robots. No, create a system that processes the whole thing, already thinking on robots or being automatically completely the whole thing, which then it's easier to process, for example, from a AI point of view or even just regular algorithmic processing. So that's it. I'm going to show you a very short video, and then we can discuss a bit more questions if you have.
Hi, I do architecture and urban planning.
I do conveying.
I do future scenarios.
I do architecture and graphic design.
Life support systems.
Chemical engineering.
Space psychology.
I do architecture.
Mining and rock mechanics.
Fashion and art.
I'm an astrophysicist.
Architecture.
Astrodynamics.
In-situ resource utilization and manufacture.
Architecture.
Brain-computer interfaces.
Space engineering.
Architecture.
Planetary geology and geochemistry.
I do economics with fish.
I do planets.
I do rocket science, and we are Sonnet.
Bueno, molt bé. Sorry. This is the team. A lot of people participated here. You have seen some of them in the video, and then yeah, I'm happy to hear questions or discuss whatever you want. Thank you.
Sure. Thank you so very much for this very nice presentation. And I think, well, I guess that as it happened to me, there are lots of things that came into your mind about sustainability, but also let's say what it means, no, to start this kind of project. And I invite everyone to make questions. You can either, let's say, write them on, type them on the chat, or just activate, unmute yourself and ask. And yeah, there is one coming. First, I would like to ask you if, let's say, because I think it's mandatory at this point, let's say, because of the confinement that we suffered and in the pandemics, did it change your vision on doing this kind of settlement, which is, let's say, intrinsically confined?
Well, intrinsically confined, not really, not really. Yes, the environment is encapsulated, but it's not confined. These spaces are very large. So this is not like a submarine where you have your rooms and you move through corridors. The idea is actually you create these volumes that are large, and then you build things inside. And we were thinking this is accounted for. There are some of these cylinders, which are even a bit larger than the standard 10 meters diameter, can be 20 meters diameter, which are filled basically with nature. And you can go there, and this has to be like this. The architects, because there were architects here, they really wanted to have spaces for people just go there and be outside in a sense. Of course, you cannot go to the surface. at least without it's not so. Another thing, Mars surface, it's the only thing that it's really dangerous that kills you immediately is the pressure. But the radiation is not that bad. It's just that you cannot stay there continuously being exposed for weeks, let's say. So you can still go outside and drive, let's say, on the surface and make a tour to see mountains. It's not that terrible along those lines. But again, the spaces is not about confinement in things that you go from your room through a corridor. No, it's very large space, and actually the walkable volume is hundreds of kilometers through the city. So you can run all you want as well.
So we have a related question somehow that comes from Luis, and then we go to Francesc, who is asking also for asking something. So is it planned to build some replica of those city habitats on Earth, as Luis Fonseca is asking?
Is there a plan? This is what we would like. So if you know a source of funding that it's ready to put the money on the table, actually it's not that expensive, and it's not that expensive in the same mindset that when you think about how much this city would cost, it doesn't cost much. It costs money, but the only thing you need to do is start it, because the idea is that you need to make the design, and the design takes time, and this is what we would need to do now to be able to be sure that the city, the infrastructure can make all its parts. Essentially, if you can fabricate everything that is inside your infrastructure, that also means that you can copy yourself, and then therefore you can grow. That's kind of really the naked essential condition that needs to be satisfied. And this can be tested on Earth. And once you have, the thing is that, yeah, it may cost you 10 millions to set up an infrastructure and do it, but then the thing goes by itself. You don't have to put €1 more, because the people there, in principle, you also design for them to get their own food and and so on. So yes, we would like to do demonstrators. There are ideas. There are people that are doing simulators of Mars, but these are mostly just to put people in psychological conditions of confinement and doing experiments of how to do operations. But there's no really a city infrastructure that it's not only a place to go, but also that it's able to develop itself. That would be our, let's say, long-term goal in the next decade, to try to actually do one or more of these demonstrators. Here on Earth, we can go to Sahara or to the Monegros or whatever, or to a strip mine here near Barcelona, where the thing needs to be regenerated, and we can try to design something there and start there. That would be ideal. If we go for that, for sure we will need a lot of people and a lot of collaborations, and everyone will be invited to participate somehow.
Well, somehow it could be adapted. Let's say the settlements in the Antarctica, no, that are used for experiments. If they could be somehow adapted, you already have some infrastructure there, no?
Yeah, but it's very expensive going there. Antarctica, in a sense, is more hostile than Mars. The wind, the conditions are very. I mean, Mars is the temperature and the pressure, but everything is very regular. Antarctica is very aggressive. The winds and the temperature and the contact, the things are changing very in a relatively. Let's say if you want to do a demonstrator, actually you don't need to go to Antarctica, I would say. That would be my message here. Yeah.
Okay. So we will move to Francesc. You can yourself unmute yourself.
Okay. Thank you, Guillem, for this very nice and exciting talk and these wonderful images that you show. My question is about the windows. I mean, I wonder how efficient are going to be these windows, because at the end of the day, I mean, it's the windows filter part of the light. So, I mean, it's not a substitute. I mean, you show this image with UV lamps for the plants and so on. And then I wonder if it will be more efficient just to have a kind of windows of virtual reality, right? Because at the end, I mean, it will be even more appealing, and take into account that in 10 to 20 years from now, maybe virtual reality will be even more advanced than now. So is it really useful? I mean, these windows, or with some kind of virtual windows, you will make it better, more robust, and more let's say, immune to radiations and so on?
Yeah, no, the radiation is, let's say, the problem I see more severe on the windows is not the radiation, because also most of the radiation doesn't even come from the sun, comes from the whole sky, actually comes from the vertical direction where the atmosphere is thinner, and then you get unfiltered gamma rays and X-rays. So as long as, let's say, your head is covered, you can look at the horizon. It's not that even the sunset is not terrible for radiation. So it's not that severe in that sense. You cannot be continuously on the surface. That would be problematic. But so getting the light in, if it's horizontal, is not problematic. But the pressure can be an issue, because then you need to build very thick windows with or then you need to use advanced materials. There are materials that can do that with fibers that give you a very high strength. But it was really considered from the architects and urbanists, people, that we need to have access to direct light, and not only light, but the landscape, the real one. As a scientist, I would agree with you. We could work with virtual windows, but as a person, also, I see the advantage of being able to go there and see what's going on outside and the valley and things like this. So it's not a very large fraction of the surfaces, because you have, the tunnels are long, let's say 100 or 200 meters long. And actually the natural light is only in the first 20, 30, 40 meters anyway. So yeah, I would not say that the windows are problematic at this point, and you don't gain much by removing them, I would say.
Okay, thank you.
So maybe Elizabeth, Ellie.
Thank you. You can hear me?
Yes. Yes.
Okay. Thank you very much for the wonderful talk. I realized that this space is not only sending rockets, it's more about Plaza Arda. I love that. And if you let me do 2 questions, because, well, I have thousands, but I would say just 2. The first one is that I understand that you cannot bring everything with the rocket or whatever you have to manufacture there, but I think that at least you have to send some things, no, to start. But my question is, there's a plan or there's a solution in the meanwhile to live there? Because you have to send the people there and start to manufacture all of that cities. So there's you have think about a plan in the meanwhile.
Yeah, so it's a bit the issue with the starting the seat infrastructure. So you need to deploy 6 or 7 people or 10. I don't know what's the number. That's the number. We need to figure out what's kind of this initial seat that. It has to be transported. Yes, at the beginning you need to put something there. It's like a seat. It's like when you put a plant, you need to put something. And how large this seat needs to be to support the few people that these people can be very strong and very high quality people also. It doesn't need later it can be more relaxed, the immigration. But let's say that would be highly trained people for a couple of years, can have a bit tougher conditions, and then start to deploy the infrastructure. This initial phase and this initial seat, that's a bit of the thing that I didn't discuss at all, and that would need to be solved. This is what needs to be solved, actually. Because if this seat is able to replicate itself, then that's it.
And the second question related to that would be that if you mentioned that these people has to be, well, smart or whatever, no, and has to be but you say at the beginning that there's need to be like attractive, no, to go there. If you cannot enjoy the nature because it's so hard, I mean that you have to be like confined, as Gemma said. What could be the attractiveness to the people to send it there or to wanted to be there?
Well, I don't know. People live in New York or in C. I don't know why or how they
for business.
For business. Of course,
start a new world, no? Okay.
Yeah. No, I mean it happens here. I mean, people can have a lot of motivations to move to places. I fully understand that. I would think that most of the people would like to go outside and do things. So of course you cannot do that in the same way you could do on Earth. We actually added these very big spaces to enable this. And it is included in the budget. It's not like, oh yeah, we will have parks. No, we put the cost of the parks and the dome. So it's there and it's in the budget. And actually it's not a problem. You could have twice the number of parks because at the end, the parks are not really that expensive. The most expensive things is the infrastructure itself. That's a good thing. If you manage to build infrastructure, let's say the welfare state, it's very cheap. You could scale and you could have actually more volumes that are only for space for people to walk and as large as you would like. So that's a good thing. But then the other thing, there is people that want to travel and change cities and explore and experience new ways of living. And the society needs to be very different from the values because you need to rely on the neighbor. It's a need. It's not a nice thing to do. Like it's here on Earth, it's nice to be good to your neighbors. No, there you have to. You cannot. You have to contribute. You have to be a collaborative individual. Otherwise, it collapses. And when it collapses, it does it very quickly. So there is not much more. There's not margin. People that go there know that. And but you have here, for example, on Earth, you have these eco-aldeas and these ways of living, and these models kind of work. And there is people willing to do it, and a lot of people, like myself, probably would like to try it. And maybe I would like it. So I'm not saying. So there's not only the incentive of living in nature that could move people there. Being in a society that's more egalitarian from default, that doesn't have historical inertia into certain ways of operating and capitalism, let's say, that it's too brutal. That would also be very appealing. I mean, people are crossing the Mediterranean to just live in the suburbs of Barcelona with no job, right? So I would think people would sign for a house, 40 square meter house, food and shelter, and then of course they have to work. But then the society is a bit more egalitarian. So I would not think that there would be a lack of volunteers.
Okay, thank you. Very nice talk.
I think we could be, let's say, debating quite a lot, and maybe we can organize a second round on that, more like participative. There are a couple of questions here in the chat, and then there is another. We don't have more time. I'm telling this to you all. We don't have more time because at 12 we have to finish. But I will. You can read. Sunil is let's say. Acknowledging your wonderful talk and is asking about the possible solutions to improve living conditions related, like it looks like a bubble. Then Daniela has another question, and then there are two more. So maybe with the first one, with Sunil's, you have seen in the chat. You want to say a few words on that?
Very quickly. So what would the Martian do for living? So being very realistic, this city would be like the main business is construction and development. So it's not your utopic scientific community. I mean, it's by need, at least at the beginning. Later on, when it grows and you want to stop developing, is fine. And then there was another comment. Looks like live in a bubble. Yes, there are possible options. The volumes here are cylinders. The volumes could be different. Then it's a matter of your favorite architect, what solutions they have. I think underground is always favored for a number of reasons that I already mentioned, but you could have another way to do it. For example, making like dishes. So you make a hole, you make a large surface, and then you put the land back on top, and that helps you to keep the pressure and creates also very large volumes that it's easy to build. So that would be another option to create very, very large spaces. So you can be creative and try to think different solutions. We just implemented, at some point you need to to make a feasibility study, you need to put one solution. And we went for this one, but yes, there are other options for sure.
Yeah, so maybe Daniela, if you want to ask, maybe it's.
Thank you. Thank you for the really good talk. I'm still concerned about the first stage of the project. I mean, what about the health of the people that arrive first in the planet? You said that in the project there will be protection of the radiation, space radiation, but they are arriving from a long trip in the space without any natural protection, and maybe they will not arrive so healthy like we would like. So did you consider medical equipment and stuff in all this situation, because maybe people they don't arrive so healthy and they don't be so healthy in the first stage.
Only superhumans are allowed.
Yeah, only superhuman. I mean, I don't know really. I mean, you need to take into account into the initial mission for sure that the people arrive healthy. You could centrifuge the spaceship when it goes there. So, well, doesn't matter. The gravity is always the issue on space, and then the radiation. But the gravity, I think, is the worst. It's only a matter. So also, don't think about the mission that people arrive there with a rocket and there is nothing. So the idea of this initial mission would be very different. What you do is you ship everything with rockets automatically, robotic, you land everything, and when you know that everything is working, then you send the crew. And when I say everything is working, when we have now these new rockets, actually this technology is happening. These are the Starship rockets that you see every couple of weeks in the news, because they are getting there. These rockets should be able to deliver payloads of around 50 to 100 tons on the surface of Mars. So with 50 tons per launch, in 3 or 4 launches, you have a lot of infrastructure already deployed on the planet, even full habitats. And when these people arrive there, they just arrive with the rocket and then they run into the habitats. And this would be relatively comfortable places for these initial people to be there. Even if, and the first thing they have to do, for example, probably is take a shovel or a machine and put ground on some of these habitats to be able to protect from radiation and thermal issues. But that's really the only urgent thing that you need to do if you have some minimal habitat there. But again, think about the thing, it's not arriving there with nothing. You first would send automatically and test all the technology that is working for the people to arrive there in reasonable conditions and start working when they arrive there. It's not solved. So that's the key issue. If we had this problem solved of the initial infrastructure, we could start Mars settlement tomorrow, because then the technology to make it self-sustainable is there. The only issue is that it requires a lot of power and a lot of automatization, but it's not a factor of 100. It's about the factor of 5 to 10 more than what we usually do here. And on Earth, nothing is optimized really for automatization. We are improvising self-driving cars on streets that are not designed for self-driving cars, and it's very messy, all this transformation. But on Mars, when you can put it from the beginning, that would probably you can get this 10-factor fold done relatively easily.
So do you think we have time for the 3 questions that we have at this time in the chat?
Which ones?
We have from Walid Khalid. Wouldn't such a model of a small group of highly trained people going first and creating everything create a structure of hierarchy in the long run from the people who were the first?
Yeah, probably. Yes. Maybe these 10 people that go there, they can come back and be heroes on Earth, but on Mars, they don't need to live there. I don't know. Or they can be given some senior positions, but not take any more responsibility after some time. I mean, if you like these kind of things, I'm very much influenced by a novel from Kim Stanley Robinson. It's called Red Mars, which basically discusses this initial step, how you start this. And there are 100 people that are sent there, and these people are like idols for the whole thing. Doesn't mean that they are, but it's about all the sociopolitics, the technology, the relations with Earth, the geopolitics, independence, not independence, exploiting Mars or keeping it in their primal state. So if you really want to see a bit more, not from me, but from a bit more detailed and well thought process, read this book. It's very good.
Mm-hmm. The society model, no, which is the starting one, and yeah.
Yes.
So then from Luis again, what a Martian would do for a living? Would a sustainable Mars require a much different blend of professionals than the Earth? And then there is another one. So the following one is, you said that technology for going to Mars is already here, and it's just a matter of money. Is it really like that? So maybe the second is.
Yeah, the first one I already answered. The Manchester will do because I read it before. It's just a matter of money. No, it's a matter of what's called, I think, it's a matter of money, but also of industrial scalability and innovation. So here we simplify, and technologies become really feasible when there's an incentive. And on Earth, the incentive is to make money. Mm-hmm. On Mars, now you cannot make money on Earth to make a process that will produce metal on Mars. There's no business case. So that's the only thing. If you were on Mars and you were there and you were able to sell your iron to somebody that then uses the iron for another thing, that would happen. It's not a matter of money, really. It's a matter of scaling the technologies that are relevant. It happens that the technologies that are relevant are the same ones that we should be using on Earth. That's the other issue I didn't touch much. But the process of extracting iron from the rock is, iron is the easiest metal to produce, and it's actually the one that is less contaminant in terms of extracting it. It's everywhere. It's very abundant. We are not going to deplete iron anywhere anytime soon. These processes, the ones that we need on Mars, we cannot use oil, and therefore you have to use processes, for example, with hydrogen without carbon, and they are being developed on Earth, and it's the same technology. That's also the thing. This city on Mars, if we have this demonstrator, it's also an incentive. There's no economic incentive for the industry to go to, it's called hydrogen thermal reduction with hydrogen of iron. This process is there. It has been there for 20 years, but there has no been incentive in the industry to actually do this. So it's a bit of the excuse to make this demonstrator of a circular economy city process, and that only uses local resources and everything is cycled, that we could actually do it on Earth. It's a matter of money to fund this, but it's not only the money, it's the incentive, let's say it. And we have the incentive now also to save our planet, right? So I think it's very well aligned. We have a lot of hope into eventually being able to fund one of these demonstrators, because I think it makes a lot of sense for a lot of sustainability issues.
Yeah, well, this circular thing, right, is kind of a key issue.
Yeah.
So yeah, maybe we cannot, let's say, continue longer, but we would like to thank you again for this very nice talk, and also, let's say, the debate. It was super interesting, and maybe we can repeat it another day. And we hope we will also, let's say, bring some speakers to ICE. So yeah, we hope we will see again. So
See you. Thank you. I'm very nearby, so when we are back in September, we can do like what's missing here, so with food and coffee, and then just chat about it. It's a lot of fun. It's a lot of fun also from your expertise. I'm pretty sure that we have a lot to learn.
We would love to. Yeah, thank you very much, and thank you all for being here. So see you next.
See you. Thank you.